Okay, so for this learning target, we need to go back to a previous learning target where we learned how to multiply special binomials. A lot of you forgot this and you just started doing the box method to multiply these, so I'll show you the box method for the first one, but then I kind of want to remind you of what this shortcut is, because we are going to have to reverse this idea, just like we did the last learning target. So if you'll notice in all three of these examples, the first term and the last term are the same in both binomials, right? You've got an x in front in both of them and a 4 in back for both of them. The only difference is a plus and a minus. Same thing for this one. You've got a 5m and a 5m in front and then a 1 and a 1 in the back. This third one looks a little scary, but it's the same pattern. 2a in the front, 2a in the front, 3b in the back, 3b in the back. So this is called a special binomial. It has this pattern in it. So we need to recognize these special binomials. So let's take a look at what the answer is to each of these, because the answer to each of these is also kind of special. So I'll first show you the box method, because I know a lot of you have forgotten. So we'll do this first one, x plus 4 and x minus 4. So I get x squared here, 4x here, negative 4x here, and then negative 16. So you'll notice that this thing, when you combine like terms, 4 minus 4 actually cancels out. So these go away, and I'm left with the x squared minus 16. Let's try the next one and see if we can see something, a pattern between them. So 5m plus 1 and 5m minus 1. Oh, I'm sorry, I wrote that down wrong. Okay, 5m and 1, 5m minus 1. So 5m times 5n, is 25m squared. I need to make this box bigger. Let's make the box bigger, because that's not going to work. Okay, so this will be 25m squared. This is going to be 5m. This will be negative 5m. This will be negative 1. Notice the same thing happens here. I have 5 minus 5, so these get canceled out. So I'm just left with 25m squared minus 1. So this is the pattern, okay? We've got, see these first two numbers x? And this becomes x squared. See how this is, the first numbers is 5m? It becomes 25m squared. So really what you're doing is you're squaring the first term. Okay, it says 5 squared is 25, m squared is m squared. Okay, so that's the pattern for the first term. You just square it, the whole thing. For the last term, I've got a 4 here and a 4 here, which turned into a 16. Notice that 4 squared is 16. Here I've got a 1 and a 1. 1 squared is 1. So you square the first term and the last term. And then notice they each have a minus sign. So then you're going to put a minus sign. Okay? So if I look at this third one and the pattern holds, then without even drawing a Punnett square, I'm going to square this 2a. 2 squared is 4, a squared is just a squared. And then the last term, I'm going to have the 3b. Well, 3b squared is just 9b squared. And then I just have to put in my minus sign. Without doing a Punnett square, without doing any of that, I know that this rule is true. Okay? Now, and this is what we learned in that way learning target ago. I already taught you this pattern. I'm reteaching it to you right now. We learned this. So the whole theme in this unit, the idea of factoring, remember, is reversing this process, right? So what I want us to be able to do is I want us to be able to start with this thing right here, and I want to turn it into this thing right in the beginning, right? I want to learn how to reverse it. Okay, so it's really important that we be able to recognize this thing. Okay, and this thing, this 4a squared minus 9b squared, this 25m squared minus 1, this x squared minus 16 is called a difference, because it's subtraction, of perfect squares. Okay, a difference of perfect squares. And I'm going to show you why it is called that. So I'm going to move the slide here to this part right here that says it's super important to memorize all the perfect squares so you can recognize them. Okay, it's the recognizing them that's a really struggle for most students, is memorizing all of these numbers. So I'm going to show you the first 20 perfect squares. There's an infinite amount of them. And all a perfect square is a number that when you take the square root, you get an integer. So the first perfect square is the number 1, okay? Because if I take the square root of that number, I get an integer. The next perfect square is 4. Because if I take the square root of 4, I get the next integer of 2. Then we've got 9 is the next one, because when I take the square root of 9, I get 3. You with me? Then the next one, I bet you could guess. If I keep going down the line here, then we can come up with all these perfect squares on our own. Now, if you're taking a test or a quiz, you could do this on every test or quiz you take. You could write the numbers 1 through 20 and square them all and get these answers, right? 4 squared would be 16, 5 squared is 25, 6 squared is 36. So these numbers right here are the perfect squares. I'm going to use the highlighter here. These numbers, the 1 is a perfect square, the 4, the 9, the 16, the 25, the 36. Those are perfect squares. And notice that when I go back to this slide right here, do you see how 25 is right here in front and a 1 is right here? Well, those are two perfect squares, right? The square root of 25 is 5, which is what we had in the beginning. 4 is a perfect square. 9 is a perfect square. 16 is a perfect square. And even things like m squared, x squared, a squared, and b squared, those are perfect squares because guess what? When you say x squared, you have that squared in the name. So you can recognize a difference of perfect squares because you've got a perfect square in the front and the back, and you've got this minus sign in the middle, which is the same thing as saying difference. Okay? So I'm going to go ahead and we're going to finish filling these out so you can recognize these numbers. I'm going to go ahead and pause the video and fill them all out, and then you can copy them down so I don't waste your time. Okay? So in a second you're going to see the slide switch and all of these filled out, and you can just copy them down. Okay, so I'd like you to be able to recognize the first 15 perfect squares. Okay, I'd like you to recognize 1, 4, 9, 16, 25, 36, etc. All the numbers I've highlighted. Normally, you're only going to see about the first 10 to 12. But in our practice, you might see the 169, 196 right here, the 169, the 196, and the 225. Those might come up in our practice. So you can always use your calculators as well to test these. Just put the 15 squared into the calculator and you'll get the number. But it's the recognizing them that's hard, right? If I give you a practice problem and I say, hey, is this a difference of perfect squares? You need to be able to say yes or no. That's the tricky part about this learning target. Okay, so let's take a look at practicing factoring of these difference of perfect squares, of reversing this process, right? Starting with the answer and getting back into the parentheses part. Okay, so step 1, make sure you have an actual difference of perfect squares. Okay, so to do that, look at the first and last number here. I'll use a different color. So my first number is 4 and my last number is 9. Are those perfect squares, 4 and 9? Well, let's go back to our list. Yep, right here is 4 and right here is 9. So I've got a difference of perfect squares because they're separated by a subtraction sign. So awesome, I've got a difference of perfect squares. The next step is using this shortcut we have, right? So a squared minus b squared. So that's what I have. I have a squared minus b squared. So the trick that we have here is all you have to do when you factor is take the square root of both of these. So the first one, 4, the square root of 4 is 2. So you're going to put a 2 in front, 2 in front. The square root of p squared is just p. So you're going to put I should be writing this down right here. So you're going to put a 2 here and a 2 here, a p here and a p here. And then the next step, and I'm going to rewrite this up here. Sorry, guys. This should be a. And then all you have to do is take the square root of the last term. So the square root of 9 is 3, so we put it in the back, and then we just put a minus sign and we put a plus sign. You'll notice that that's the exact same pattern we had in the beginning, right? When I started with 25m squared minus 1, what's the square root of 25? It is 5. Let me use a different color. Right? Square root of 25 is 5, so both 5s went in front. Then m squared. I have an m in front, m in front. And the square root of 1 is 1, 1. Right? The second one works too. What's the square root of 4? 2 and 2. What's the square root of a squared? A and a. What's the square root of 9? 3 and 3. What's the square root of b squared? B and b. And then plus and minus sign. Okay? So that's always going to be true as long as they're actually squares. So let's go ahead and do the next one. Well, you could always check your work, by the way. Like if you aren't sure, you can always, okay, look, I got this answer. Let's check and see if it actually works. Now, you don't have to do this. This is just a check to make sure you're doing it right. But you can put it back in your Punnett square and make sure that you do actually get that beginning answer. Oops, it's a 6. So these guys cancel, and you end up getting 4p squared minus 9, which is what we had in the beginning. This is your answer, but you can always check your answer and look back, okay? So that way you know the rule works. So, okay, number 2. I'm going to factor this like this. I know that's my skeleton. Square root of 16 is 4, so I'm going to put a 4 in front, 4 in front. I've got an x squared, so that means x in front, x in front. And then 1 squared is 1 and 1. Put a plus in one, a minus in the other. It doesn't matter the order. You could put a minus in front and a plus in the back. It doesn't matter. Second one, check to see if they're perfect squares. Is 64 and 16 perfect squares? Well, let's go back to my list. Look for 64. Yep, it's right here. And 16 is right here. So I've got perfect squares. So I can use my trick. Parentheses, parentheses. The square root of 64 is 8. So 8 in front, 8 in front. I've got an x squared, so x here, and the square root of 16 is 4, 4 here, put a plus, put a minus. Okay? So not terribly difficult. Again, like I said, the difficult part is making sure you have a different as perfect squares. For example, something that is not a perfect square binomial would be something like if I had 6x squared minus 4. When I look at this right here, I'm going to check to see if these are perfect squares. 4 is a perfect square, so cool, 4 works. But 6 is not a perfect square. If I go back to my list, the square root of 6 doesn't come out to a whole number. It's not on my list, it comes out to a decimal, so this right here is not a perfect square trinomial. Even though it's got this minus sign, this is not a perfect square trinomial. You cannot use the trick for that one. Okay. So on this next page here, this you try, I want you to go ahead and pause the video and try to do these 3 examples. Okay? Alright, so these should be your solutions to these 3 problems. So the first one, 81 and 4 are perfect squares. So I get 9r in front and I get 2 in back. Okay? Second one, 25n squared minus 36. Both of those are perfect squares, so I can do 5 in front and 6 in back. Okay. The third one is when you check out 72 and 2, they are not squares, so you might first think that this cannot be factored, right? Well, this kind of leads me into the next part of the learning target. So, you know how we did the GCF in the last learning target? Well, I hate to break it to you, but like I said, this GCF idea is going to come up in every learning target. So we're going to come back to this guy. This guy right here, we're going to come back to it and see what we can do with it. So let's talk about this idea of a GCF. The really tough part about factoring, really tough, is that each lesson builds. Every single time we factor something and reverse that process, we always have to check for a GCF first. I don't care what you're factoring. I don't care if it's a difference of perfect squares. I don't care if it's something we have later in this unit. You always have to check for a GCF. So, the directions for every problem in this unit is going to be factor. Just boom, factor each polynomial completely, right? That's what this direction says. It doesn't say factor the difference of perfect squares. It doesn't say find the GCF. It just says factor completely. So it's really important that when you look at a problem, you follow these steps and be able to recognize how the problem looks. Okay, which is really the hardest part, guys, being able to recognize it. So when I look at number 1, I'm going to follow this rule of check for a GCF first. So in number 1, is there a GCF between 24 and 6? Yes, I recognize a 2 between them, but I also recognize that 6 is bigger than 2. So I'm going to go ahead and pull that 6 out. So I've got 6. When I pull the 6 out, I'm left with 4x to the third and then minus x. Now there's something I forgot here. Is there another GCF, another factor between these guys they share? Absolutely. Notice they both share an x. So I'm going to go ahead and go back, and I'm going to realize that my GCF is actually 6x. So when I put back my what's left over, I've got 4x squared minus 1. And now notice, guys, this is the hard part. This is not your final answer like it was in the first learning target, because now we can go one step further. Oh, oops, I didn't mean to do that. I thought I had the highlighter on. Let's try to rewrite that. Okay, so now when I get this guy, I'm going to ask myself, okay, are these things in here perfect squares? Is 4 a perfect square? Absolutely. Is 1 a perfect square? Yes. Is there a minus sign between them? Yes. So this is a difference of perfect squares, meaning I can go ahead and factor this further. So I'm going to bring down the 6x, I'm going to make my skeleton, and then I'm going to use my little rule. The square root of 4 is 2, so 2's go in front. Square root of x is x and x. Square root of 1 is 1, and then put a plus, put a minus, and this entire thing is your answer. Okay? So not every problem's going to be like that. All the ones in this learning target for the most part will be, but as we continue to go forward, they might not be. You might take a GCF out and be left with something that doesn't look like a difference of perfect squares. So let's go back to this problem that we said weren't squares. So 72 and 2 are not perfect squares. Nope, they sure aren't, but does 72 and 2 have a GCF? They sure do. They have a 2 in common. So when I pull out that 2, I'm left with 36x squared minus y squared. Now this looks weird, but if you have a squared, that's still a perfect square in the variable. So this is going to look like 2 times 6x minus y times 6x plus y. So just because it initially looks like it can't be factored, you really have to recognize those perfect squares, which is why I said in the very beginning, this list of numbers right here should be something very fresh in your mind. All right? So let's go ahead and do a few more examples of this GCF idea. So number 2, does 63 and 28 have a GCF? Now, this might be a little challenging because 63 and 28 are annoying numbers. They're kind of big and it's not obvious what the GCF is. So I have kind of a trick on the calculator to show you that makes your life much easier. Okay? So on our calculator, I'm going to go ahead and this is kind of a couple step idea. The calculator will actually tell you the GCF of two numbers. It's kind of cool. So if you turn on your calculator, hit on, you're going to click this math button right here. Okay. Now we've used the math button to work with fractions in this menu. Well, now we're going to move over to this number menu. So hit math and then move your cursor over 1 to the number menu. Okay. Then I want you to scroll down past 7 and scroll down all the way to 8 where you see this GCD. It doesn't say GCF, it says GCD, but this is what this is going to help you do. Go ahead and hit enter once it's highlighted, and you're going to then get this GCD parentheses. In the parentheses, you're going to type in 63, and then the comma button, which is right here, and then 28. Don't put the negative in. You don't need the negative. Close the parentheses and then hit enter, and it's going to tell you the GCF is 7. Which means you don't have to think about that. You can just use your calculator to get that number. So now I can go back to my problem and go ahead and use my little rule about difference of perfect squares. So now I know the GCF is 7, so I'm going to pull that 7 out. I'm left with 9. Oh, wait, I also have an n. See, I forget that too. They each have an n in common, so I can pull out 7 and n. I'm left with 9n squared minus 4. And I just noticed here that 9 and 4 are perfect squares, so I can go one step further and do 3n minus 2 and 3n plus 2. Okay? Number 3, 909, you can put in your calculator. I know that they both have a common, the GCF is 9. I'm left with 100x squared minus 1. I know that 100 is a perfect square, so that's going to leave me 10x minus 1, 10x plus 1. You start to do this enough, and it's going to become second nature. All right. And finally, the last one, I've got 81 and 100. Now, I wouldn't be 100% confident that these don't have something in common. I do recognize they're perfect squares, though. And my gut is telling me it's going to be 9 and 10, but I'm not like 100% sure, maybe. So I'm going to go back to my calculator. I'm going to go ahead and go to math, number. You can also just hit 9 to get the 9, and it'll pop up if you want to, or you can scroll down. 81, 100. Parentheses, hit enter, and it says 1, which basically means they don't have a GCF. So I'm going to go ahead and just follow my rule of my skeleton. This is going to become 9n, 9n, minus 10 plus 10. Okay? So I've got 4 more problems for you to do on your own to try. Again, if the numbers are big, go ahead and use your calculator, no problem. And then when you unpause, I'll go ahead and show you the solutions. Alright, here are your 4 solutions. Please go ahead and check if you're correct. If you're not, you know what to do. Please come talk to me and I'll help you get that figured out. There's one last thing I need to tell you, and it's not too crazy complicated, but it is something that's going to come up. Sometimes we have polynomials that cannot be factored. There's no GCF, no difference of perfect squares. They just are what they are, and you have to leave them. We call these polynomials prime. And we call them prime because all of the numbers in them will be prime numbers, right? So when I look at 7x and 19y, 7 and 19 have nothing in common. X and y have nothing in common, so I'm just going to write prime. Same thing with this guy. This has a 2xy, this has a z and a 5, and this has a 1. None of them have anything in common, so I'm just going to write prime, which is basically a fancy way of saying I can't factor this thing. It just is what it is. I can't turn it into a multiplication problem. Okay, so that's basically it for this learning target. Again, this is going to be something that comes up in the next one. So you cannot just do a learning target and then forget. Okay, so take it seriously, feel like you're mastering it. All right, good luck, and come to me for help.